I'd like to introduce myself. My name is Chihiro Sagai. It sounds like Chihiro, Napolitano, but I'm not Napolitano. I joined Kimica 4 years ago as a logistic expert. I have an experience of 10 years logistics, and 2 years ago, my boss asked me and assigned me to the sales team. So now I've started working as a sales just 2 years. I'm quite new, so I understand your concern because I'm kind of fresh, but I have a perfect support such as Jim and Kurt. They will give you excellent presentation later. And my market is Italy, France, Spain, Turkey, and also some Asian countries such as Indonesia, Malaysia, Singapore. Now, I will go to company profile. Our company, Kimica Corporation, established in 1941. Our president is Fumiyoshi Kasahara, our company is a family company. Business is only alginate production and sales. And our office headquarters located in Tokyo, just front of Tokyo Central Station. And also we have a plant in Chiba. It's a countryside, like 50 kilometers from the Tokyo. And also we have Osaka branch and Santiago office in Chile, and also Pine plant. This is also located in Chile. And now we have Kimica Europe office located in Düsseldorf, and warehouse is located in Rotterdam.
酒井さん、スライドが変わってない？
変わってない。今動かしてるんだけど、見えない。今どこのスライド？
千尋酒井って書いてあるやつ。
本当？
顔写真のやつ。
止まってる？
止まってる。
これも動いてない。
動いてない。
なんでだ？まだ動いてない。
動いてない。みんなは見えてんのかな
？Salad, do you see my new slide? My slide is changed?
No, it's still the same, Sagai-san.
Oh, 見えてない。
Maybe taking a little bit longer.
Nothing changed?
But I think you can keep going and talk and explain anyhow. Maybe the line is not excellent, but I think you can go on with the presentation anyhow.
Okay. So Kimica has devoted to alginate for 80 years. We are alginate professional company. I'd like to show you our slide, but I think you don't see
No,
my
now they're going. Now they're coming.
Okay. Okay.
Yeah.
So here's alginate manufacturers in the world. In Japan, 3 companies was working as a alginate manufacturer, like Kimica, and Kikkoman Biochemical, and Fuji Chemical Industries. But Kikkoman already stopped to producing alginates, so actually in 2 companies now. And Japan and JLS and Algaia is very famous in Europe, and also big company Bright Moon in China. And Kimica and Japan, only the companies for we have all the grade for industry and food, and also pharma and medical. This is a transition of alginate manufacturers in the world. Now, there's so many transition in the world. It's not only overseas companies, and also in Japan is the same. Kamogawa Chemical is finally Kikkoman Biochemical, but they already stopped. And Tohoku Chemical turns to Fuji Chemical Industries. And Kimica is unchanged. The name only the name has been changed. Kimitsu Chemical Industries, renamed Kimica in 2011. And Kimica keeps growing. In last year, our annual revenue was 8.2 billion Japanese yen. It's meaning $76 million. And we keep growing almost 2 to 4% per year. Kimica is the only company maintaining historically unchanged in the world. It means we are a very stable company. This is alginate application and the volume balance ratio. The most major application is industrial grade. This is for like textile printing as a thickener. And for food, several applications such as bread, noodles, cakes, many applications. And we also have the medicines. Here's a detail. For food, alginate is used as a thickener, gelling, stabilizer, dietary fiber, noodle, bread, beverage. And for industry, as I told you, it's for fabrics, textile printing is major application. And also for pharma, it's very famous as a wound dressing and like a Gaviscon antacid medicines, and also dental impressions. Here is the world alginate market. It's Europe is a very big market in alginate. It's the same as North America and Asia. Grazie mille per l'attenzione.
Thanks, Chihiro. Any question for Chihiro and for her presentation? Otherwise, we can switch to the presentation of Dr. Jim Gregg about the alginates and their properties. So we can start with Jim, I think. Thank you.
Okay, thank you.
Thank you so much. Jim, so it's your turn.
Thank you, Sarah. Good morning. My name, please, is Jim. I have many years' experience in the alginate business. If you remember one of Chihiro's slides, it mentioned Kelco, ISP, Monsanto and FMC. Well, I worked for them all. I retired about 10 years ago, and since then I have been a consultant for Kimica on alginate. This morning I'm going to take you fairly quickly through why you should use alginates and touch a little on how to use it. So let's go back a bit, and there is comments around of hydrocolloids, gums, alginates, etc. This slide here shows you essentially what all gums, all hydrocolloids do is thicken or gel water. And to do that, they need to basically be hydrated or dissolved. And to get good hydration, firstly requires good dispersion. And I know some of you who have looked at alginates before have been slightly worried about how to disperse them, but I'll, a few slides further on, I'll show you the easiest way to do this. So hydrocolloid thickeners provide different rheological properties, i.e. they change the viscosity of water, right through from very thin pourable liquids right up to gels, which are usually demoldable solids. The gums themselves really fall into two categories. Some are cold soluble and some are hot soluble. Alginate is cold soluble, so there is immediately cost benefits for using alginates because you don't have to heat up water. So let's now look at alginates. They're extracted from a brown seaweed. They've been around for over 100 years. They function both as thickeners and gelling agents. They are a coal-setting gelling agent, as we've said. There is no heat required. They also make non-melting heat-stable gels. So once you make the gel, it will not fall apart with heat. So they're good for baking and retorting. The reactivity comes from their solubility with calcium, which is also a strength and a weakness. And really, how the understanding of controlling the reactivity with calcium is the key to using alginate and the success of using alginate. So they have limited applications in really low pH systems, below about 3.8, because at that point they react with hydrogen ions from acids and will actually precipitate. There is another form, a chemically modified form of alginates called propylene glycol alginates, which will work in more low pH products, typically in things like dressings, beverages, syrups, and also as a beer foam stabilizer. Alginates have always required a little bit more technical support than some gums, and that's why we're all here today to help you. But the benefit is really they come from seaweed, so they don't have any negative implications like GMO, kosher, kosher and halal is not a problem. As Chihiro alluded to, Kimica has two manufacturing plants, one in Chile and one in Japan. And both these plants produce a range of alginates for you. And essentially the product range consists of alginic acid, alginate salts, which is predominantly sodium, and also PGA, propylene glycol alginate, and all grades for pharmaceutical, medical, food, and industrial. When you extract alginate from seaweed, the type of alginate you get is dependent on the species of brown seaweed. And nature is very kind to us in as much that certain brown seaweeds differ from other brown seaweeds, and they give us the two forms of alginate. And if you think of these like long chains, there are a long chain that has got a lot of bends in it, which you think of as high G, which forms strong brittle gels with good heat stability. The other chain that you can extract out of seaweed is basically a more long straight chain, which is called high M, after the manuronic acid group, whereas the previous one was guluronic. And they form more weaker gels. They're more for thickening and stabilizing rather than gel formation. So when you dissolve up alginate, depending on the length of the chain, you can go from a, on the left-hand side, smooth, long flow solution, but with the addition of calcium, you will go through a higher viscosity right through to a cross-linked gel. And this is done without heating or cooling. It's essentially the ion exchange reaction between calcium and the alginate chains. And for instance, here's an example of how easy it is to make an alginate gel. And in this case, we're talking on the right-hand side, the solid gel is 1% or less than 1% alginate and 99% water. And it's essentially been made by a solution of sodium alginate and a calcium salt with some sequestrant and an acid in there, just essentially to control the reaction. Otherwise, the reaction would happen instantaneously and you wouldn't be able to mold the alginate solution pre-gelation. So there are various ways of controlling the rate at which the gel will be produced. The other great property of alginate gels, as I've said, is they give unique and excellent heat stability. Picture on the left shows 4 typical gels: carrageenan, gelatin, algin, and agar. When you apply heat, 3 of them melt. However, the alginate gel, as I've said previously, once it is made, is stable to heat and will not fall apart. So this is how it can be used in foods and in medical applications. Obviously, within the thickening, we have a range of viscosity. Similarly, within the gelation, we can produce soft gels and firmer gels. And this just gives you an idea of what the gels look like. With a small weight, the ones in red shows deformation of the gel with a small weight, whereas a much heavier weight on the stronger gel shows very little change in the gel structure. And really where this is important is when it comes to the applications in terms of you've essentially 2 things to change. That is the concentration of the alginate you use and the calcium concentration. So as you go through either increasing the alginate concentration, going vertically up the graph, you can get frozen jellies from thickening. But as you add more calcium, you get to thixotropic, where you can stir the gel formation before it happens, and you get into cake toppings, jams, table jellies, and then ultimately once you add in much more calcium, you will get to much stronger gels. So really the differences in terms of to look for the use of alginates in a specific application depends on both physical and molecular. So physical, the things that can be changed are obviously the particle size, particle shape, and the bulk density. And we can supply alginates that match any of these characteristics. On a molecular level, obviously the viscosity of the solution, which is essentially comes from the alginate chain length, the M to G ratio, which is whether it's either a thickening or stabilizing alginate right through to a gelling alginate, the salt type, as I've said previously, you could have sodium, you can have magnesium, you can have potassium alginates, etc. And the level of calcium you react with. Propylene glycol alginate is slightly different in as much that, unlike sodium alginate, it's essentially non-ionic. It doesn't precipitate easily by metal salts, and so it can be used in a more acidic and calcium-rich products. And there is a lipophilic character, which gives surface activity, so you can get sort of pseudo-emulsion properties from PGA as well. So the main areas of using alginates, as I've said, and it's stressing the same thing, is thickening, gelling, suspending, foam stabilization, emulsion stabilization. And really what you're looking for is the body that it brings primarily to food, the mouthfeel. It can be made into a film, it can impart cling and emulsification. Just quickly before I finish, really want to talk about dispersion and hydration. A lot of people get slightly put off by alginate because they worry about how easy or difficult it is to put into solution. Well, it's not. Excuse me. You've got, in terms of what we talk about in dispersion and hydration, one is to disperse the dry products, the dry gum particles into the liquid, first of all, to stop it clumping. And then as the individual gum particles are surrounded by water, they will start to swell and then become a solution. So really in picture sense, you disperse them, they become wet, but they don't hydrate, and then eventually they swell and go into solution. And all three processes are essentially happening simultaneously. The things that affect dispersion are essentially the particle size of the material, the amount of shear or force you put onto the solution, and whether or not you add dispersants. In general, you don't need any dispersants. You can make alginate solutions in water very, very simply. The picture on the left-hand side shows what happens if you don't do it properly. If you just pour alginate powder into water, it all just clumps together because you haven't dispersed the particle. So you have got to use a high-speed mixer and essentially generate a vortex. So when you add the particle, you're sprinkling the particles into the vortex, and this essentially aids dispersion. An industrial scale is to use something like an inductor funnel, which essentially uses the water supply to pull the dry powder through the funnel, disperse it, and then put it into a tank with a high-speed mixer. So the vacuum that's created pulls the dry powder and disperses it at the same time. And then the mixing will, after a length of time, produce the solution. You can add dispersants if you want to speed up this process. For instance, you can put in some sugar, oil, maltodextrin. The only thing you've got to watch is obviously any presence of high levels of sodium will inhibit hydration, and also calcium. So the water quality itself is one of the things you have to look at. Soft water is obviously better, but as you move to harder waters that contain more calcium, it becomes a problem because the alginate starts reacting with the calcium essentially to form a gel-like structure. So once you have disperse the solid then fully hydrates and you get a solution. Obviously, the dispersants will aid that. For instance, the sugar will coat the particles and cause them to hydrate better. So essentially, to sum up, you know, the factors that affect hydration, the ions that are in the water, the solids, the amount you're trying to dissolve, the shear, and the particle size. And essentially, it's obviously the larger particle size takes longer to dissolve. And that's really what the graph shows, is two different particle size. They ultimately reach solutions round about the same time, but obviously hydration will take longer. So essentially, just to repeat again, the factors you need to consider when you hydrate alginates, you've got to fully hydrate the alginates before you add any other ingredients. Careful addition of the powder to water will help hydration. Obviously, high alginate concentrations will retard hydrations, and if possible, reduce the mixing speed after dispersion to stop air incorporation. It's probably more important with high ester propylene glycol alginates. And then salts and acidic ingredients should be added at a later stage. So really, to look at the alginate types, on the left-hand side, you see you have sodium alginate, which is soluble in water, can either be thickening, stabilizing, or a gelling agent. You can also use this for controlled release. There are applications in the pharmaceutical industry where a drug is coated with alginate, so as it is digested, the alginate slows the release of the drug into the body. They are more compatible with acids and high calciums. Moving on to propylene glycol alginate, they are obviously more compatible, as we've seen previously. They can be used at lower pH solutions, more acid. There is the secondary emulsification, and they are also lithophilic. Alginic acid, obviously the base of the formation of all alginates. Alginic acid is, of course, insoluble. It absorbs water and then expands, so it has uses as a tablet disintegrator. The other alginate salts that we produce, like magnesium, potassium, are obviously all soluble in water. They are much more highly specialized. I would say about 90–95% of the alginate market is based on sodium alginate. And that's it. It's a very, very quick introduction to alginates and the use of alginates. So if there's any questions, I will try my best to answer.
Don't be shy. If you have some question for Jim, he's here for you, so please.
Well, stunned everyone to silence.
It's too early. It's too early in the morning, Jim. So I will ask Kurt to make his presentation on the application of alginates.
Okay, let me introduce myself. I'm just a moment. I'm Kurt Hara. I'm manager of research and development division. Jim has a long experience with arginate, but I'm quite fresh in Kimica. About 3 years ago, I joined to Kimica. I would like to talk about the application of arginate. Actually, alginate are widely used for various industry, food, pharma, cosmetics, and so on. Today, I will show you some applications. I know most of you are interested in pharma or cosmetics, but sorry, my field is food application, so most of the slide is about food application. The first one is ice cream. Sodium alginate gelate with milk calcium and can improve the texture and can work as a stabilizer for shape retention. One of the characteristics of alginate is that alginate gel has a heat stability. This characteristic is used for stabilizer of bakery fillings. And also alginate are used for reforming food, such as onion rings, pimento of olives. Imitation foods are also made from alginate. This is an application for meat binding. Thermostable alginate gel binds meat, and these meats are not broken off when they cook. Not only meats, but fish or vegetables are available. Fat alternatives are made from vegetable oil and alginate, which is a healthy fat compared to animal fat. Alginate gel can absorb water inside, and these characteristics are used for dumpling. Noodles are one of the most popular applications of alginate. Alginate improves the texture of noodles. Bread is also a common application. Alginate increases softness and volume and improve texture and so on. This picture shows the difference between with and without PGA. It is said that PGA contact with gluten and adds the strength to the gluten structure, so the bread can keep the shape. This picture shows the reduction of oil absorption. And PGA can use for foam stabilizer, mainly for beer in South America. And also used for meringue. PGA has a oleophilic structure and can emulsify both oil and water, and it is used as a stabilizer for salad dressing. For beverages, PGA is used as a stabilizer to prevent precipitation. And also used for the stabilizer of yogurt drink like pectin. I will show you pharma and cosmetic application from this slide. These are several materials that are used for dental impression. Alginates are one of the most frequently used material. The advantage of using alginate is low cost, easy handling, short execution time, and the possibility of detecting a detailed impression. One of the major applications for pharmaceutical is for gastric coating agent. The patient drinks liquid of sodium alginate, and the sodium alginate, and the sodium alginate changes to alginic acid in stomach with gastric acid. The gel of alginic acid coats the wall of stomach and prevent from gastric acid. Wound dressing with fiber of calcium alginate has been developed. The fiber of calcium alginate absorb water and sodium ions from exudate, and alginate fibers swell at the surface of wound. The gel of alginate provides moisture environment for wound healing. Lipstick with sodium alginate gelate on the surface of lip with calcium which is formulated in lipstick. When we drink a cup of coffee, sometimes the color of lipstick will lose. In this case, lipstick with alginate prevent losing color. And this is the last slide. Sodium alginate are used for printing paste for natural textile, for example, cotton and hemp textile. Thank you for your time and attention.